All right, so we want to continue looking at increasing, decreasing critical values, but I want to throw in something that you have not seen yet, but I've mentioned, and that is that the other place that we can get critical values from, and that is from points where the derivative would equal 0, okay? And also where the derivative would be undefined. Okay, so we've only looked at ones where the derivative equals 0 so far. The one thing I will say that you have to be careful about here is you have to make sure you pay attention to points of discontinuity as well. Holes and asymptotes. Okay, so that stuff comes into play here because that will determine are we dealing with a discontinuity or a critical value? Okay? And while we incorporate all of them into a sign diagram, how we interpret that sign diagram will be different then. Okay? So, let's consider this function here. We have x cubed plus 3x squared minus 4x minus 12 all over x squared minus 9. Before we get into doing the derivative, let's first of all look at this function closer and see what we can tell about it, okay? And specifically dealing with the domain and discontinuities. All right, so if I were to factor this out, the bottom would be x plus 3x minus 3. And in the top, I would do that factoring by grouping. So I'd have an x squared times x plus 3 minus a 4 times x plus 3, if I group the first two terms and the second two terms. And then that means I would have an x plus 3 common factor, and then that would be times an x squared minus 4, which could factor further, but I've gone far enough to be able to tell what I need to. Okay? My domain for this function would be what? X cannot be
3 plus or minus 3.
X cannot be plus or minus 3. Now when you have a rational function like this and you see limits on the domain, those limits either give you an asymptote or a hole. Okay? So let me ask you here, what does negative 3 give us? Is it an asymptote or is it a hole?
Asymptote.
Why?
Because the hole would be when the positive 3 cancel, I think. No?
Okay, you got the right idea, but you're looking at the wrong one.
Is it
The x plus 3's cancel, right?
That makes sense.
And that gives us a hole.
Okay.
If it cancels out, it's a removable one, so it's a hole.
Okay.
Okay? That though gives us the negative 3 as a 0, the denominator. Okay? So here, those can cancel, so that means there is a hole at x equals negative 3. So you got to keep that in mind. The x minus 3 is left over. It does not cancel out, so that means we have a vertical asymptote at x equals 3. Okay? Now, if I'm doing my sign diagram, I need to put negative 3 and positive 3 on there, because holes and asymptotes can impact the graph, the shape of our graph. Okay? But I need to make sure I note what those are. This is a hole, and this is a vertical asymptote. Because what I don't want to do is I don't want to put them on there and then accidentally call one of them a plateau point. Because it's not even a point. It's a discontinuity. Alright? So, I'm making my sign diagram. I'm starting here by putting anything that is not in the domain on there as something that could impact the shape. Alright? So now I need to find the critical values. Critical values, remember, are where f prime equals 0 or f prime is undefined. We haven't run into one of these yet where it's undefined, but we will here. Okay? Now, here's the cool thing about this. We canceled out the whole. So guess what? When we take the derivative, we don't need to mess with that extra part. Okay? Because all it is a hole punched in our graph. It doesn't affect where our max or min points are going to be or anything like that. Okay? So, when I do f prime of x, I can take just the derivative of what's left over, the x squared minus 4 over the x minus 3. Okay, as long as I note in my head that, hey, there's a hole at negative 3, I can do this. Alright, so let's go ahead and figure out what this would be. What am I going to use to find the derivative of x squared minus 4 over x minus 3?
Quotient rule.
Quotient rule. Okay, so we got the u prime v minus uv prime all over v squared. The u is our numerator, the v is our denominator, remember? Okay, so u prime equals 2x, v is the x minus 3, minus u is x squared minus 4. What's v prime? 1. And that's all over x minus 3 squared. Okay? What's that?
Should we distribute?
So yes, this is where, remember how I told you in our previous unit that how far you simplify is going to be dependent on the type of problem. Okay? Here, we need to actually set this equal to 0 and solve it, so we're going to want to simplify that numerator some more. Okay? So let's go ahead. 0 is going to equal 2x squared minus 6x minus x squared plus 4 all over x minus 3 squared. Okay? Now, notice here the derivative is undefined at x equals 3. Which makes sense because the whole function is undefined at x equals 3. Alright? But, now if I multiply both sides by the x minus 3 squared, that's gone and I can just look at my numerator. So I simplify that and I have an x squared minus 6x plus 4. And that doesn't factor. So I've got to use my quadratic formula again to get my 2 critical points. Okay, so it's 6 plus or minus square root of 36 minus 4ac, so minus 16 all over 2a, which is 2. X is negative 6, or sorry, positive 6 plus or minus radical 20. Well, radical 20 is a 2 root 5, and that's all over 2. So this simplifies down to 3 plus or minus root 5. Okay? You guys know how to simplify radicals and stuff, so. Okay? Now, radical 5 is about 2.21, I think. So yeah, radical 5 is 2.24. So 3 plus 2.24 is 5.24. 3 minus 2.24 is going to be 0.76. Okay? So those are our 2 critical values. And now we can put those in where they belong. Okay? The 0.76 will go here. and the 5.24 is going to go right there. Okay? It's important that you put the numbers on the number line in order. Otherwise, you're going to get your intervals messed up. Okay? So now we can look at the sign of f prime to tell us something about f. All right? Now, one thing about the sign here, notice the denominator is squared. So the denominator will always be positive, right? So keep that in mind. Use that to your advantage, okay? I don't need to plug anything into the denominator because it's going to be something divided by a positive every time. So now I look at, say, a negative 4. The numerator had simplified to x squared minus 6x plus 4. If I plug a negative 4 into that, I get positive 16 plus 24 plus 4. That's positive. Positive, positive, positive. So now I know that this is positive, which tells me my function is increasing.
Wait, we're plugging this into the original, right?
No, we're plugging this into the first derivative. Because the sign of the first derivative tells us the direction of the function. Increasing or decreasing. My next interval here includes 0, so if I plug 0 into that x squared plus 6x plus 4, that's positive. So look at that, now I am increasing again, okay? Now it makes sense because that was just a hole, right? So we had a hole there, it's just going to go straight through the hole, there's just going to be that empty spot there. So now at 0.76 to 3, 1 is in that interval. If I plug a 1 in, I get 1 minus 6 is negative 5, plus 4 is negative 1. So now we're finally decreasing.
Would it still decrease on the other side of our asymptote?
That usually is the case, isn't it? Like it goes down to negative infinity, then it jumps up and starts going down. Let's double check that by plugging in a 4. If I plug in a 4, I get 16 minus 24 is negative 8, plus 4 is negative. So yeah, you were right. Okay? And that usually is the case as long as that 3 wasn't like a double root or something like that.
And then after the vertical asymptote, like at 6, it would too, so for the rest of it.
Okay? At 6, if I plug in a 6, I get 36 minus 36 is 0, plus 4 is 4. So yeah, that's positive. Okay, so we're increasing. So notice here what we have. We had a hole at negative 3. What do we have at 0.76?
That's horizontal,
Amen.
the max.
It's going to be a max. We're increasing then decreasing, right? That's a max. Then we've got an asymptote at 3. What do we have at 5.24? That's where we have a min. So using this sign diagram is actually incorporating something that we call the first derivative test. Okay, the first derivative test. There are two tests, the first derivative test and the second derivative test, to see what exists at a critical value. So let's talk about what the critical or what the first derivative test is, that you'll actually see how what we just did is that, okay? It's not anything super complicated, but just kind of a formal way of putting this together. So, and you'll be asked to do this several times. You'll be told, hey, prove that this is, or in IB command term is show. When you see they tell you to show something, it's really, prove that this is the case. When you're supposed to show something, this is what you need to do. And if we're showing that a point is a max or a min point, the first thing that we need to do is show that the derivative equals 0 at that point. Okay, so in other words, show that it will be a critical point. Right? The next thing is the first derivative test. And in the basic sense, the first derivative test simply is describing how if the first derivative changes sign at that point, then we have either a max or a min. Okay? This is not a formal statement of the theorem or the test, but this will give you the idea. Okay? If f prime of x changes from positive to negative at a point or I should say instead of a point at x equals c, then there is a what? If it's going from positive to negative, a relative max. When x equals c. And of course, all of this is assuming that the first part is true here. If f prime of c equals 0. Okay, so we've already done that part. We've found that this is a critical value. If the sign of the derivative changes from positive to negative, we have a relative or local max at that point. Okay? On the other hand, if f prime changes from negative to positive, at x equals c, then there is a relative min. When x equals c. Okay? Now, what's the third alternative?
Doesn't change.
If there's no change in sign, okay? If f prime of x does not change signs, then x equals c is the location of a plateau point.
Is that where it's called a sign diagram? A sign diagram, no, Deacreasing.
Well, it's a sign diagram because we don't really care what the value of the derivative is. All we care about is whether it's positive or negative or 0 or undefined. Okay?
That's a critically valued.
All right, so you can tell what we did there with the sign diagram and then identifying max and min points. It was really just logical. I mean, it made sense. If it's positive, we're increasing, and then it's negative, so we're decreasing. In between there, we had to peak and get a max. Okay? Yes?
If it's undefined, it's undefined.
If it's undefined, that's where we have either a hole or an asymptote. So
Okay.
that's something where the derivative is undefined.
Okay.
Yeah. Okay?
Okay.
All right, so let's think about the entire process. And right here what I want to do is actually kind of put together the process that we started learning back with pre-calc honors and do all of that stuff, and then incorporate also what we've learned now in calculus to come up with a very detailed sketch of a function, and also incorporate some additional information into this. So here we have the information that we saw before, okay? And so we've already done part of this, but just laying out this whole process here, we factor everything that we can. If you recall, this one factored so that the top was an x plus 3 times an x squared minus 4, which was x plus 2, x minus 2. And then in the bottom we had x plus 3, x minus 3. Okay? Now, secondly, we look for the easy stuff to find, okay? So, for example, a y-intercept, the domain. What do we have as far as asymptotes or holes? We already recognized that we're going to have a hole at x equals negative 3 and an asymptote when x equals positive 3. We can also identify the y-intercept. The y-intercept is when x is 0. So if we just look at these constants, we can see that the y-intercept is going to be at the point 0, 12/9 or 4/3. Okay? So 0, 4/3, there's our y-intercept right there. Okay? So the y-intercept, 0, 4/3. Drawing in the other things here, vertical asymptote was at x equals 3. There's a hole at the point negative 3 something. Now, negative 3 something, we need to plug, how do we get the y coordinate of that hole? This part we didn't do before. That's right, okay? After we cancel out this, we could go ahead and plug in a negative 3 here, and that will tell us where that hole existed. Okay? So if we plug in a negative 3, we have a negative 1 times a negative 5, so positive 5, times over a negative 6. So negative 5 over negative 6 is just a positive 5/6. Okay? So at negative 3, 5/6, we put a little hole there. We can exaggerate it a little bit. And we also have an asymptote at positive 3. So let's put that asymptote there. Okay? Now, there are other things here that we also can identify. For example, the zeros. Where would the zeros be in this case? 2 and negative 2. Yeah, look at the numerator after we cancel it out. In order for this whole thing to equal 0, the numerator has to equal 0. So the zeros are at negative 2, 0, and 2, 0. And notice here, I'm plugging things in as I go. Okay? Okay? Oh wait, hang on. The hole was at negative 5/6. Because it would have been a positive 5 over a negative 6. I got that in the wrong spot. Lost a negative there, just realized.
It's okay, Mr. Nixon.
Okay? Alright, so we've got that. All of that stuff is stuff that you did in pre-calc. Okay? We figured out all of those. In fact, there's even one more thing that we figured out back in pre-calculus, and that's because the degree of the numerator is only 1 bigger than the degree in the denominator. Since it's bigger on the top, we don't have any horizontal asymptotes, but what kind do we have? We do have vertical, but I mean, since the degree on the top is exactly 1 more than the degree on the bottom.
Isn't the bigger on
Bigger on top, there are no horizontal. What's the only kind? What?
Slant.
The slant. Okay? Let's take a moment here as an aside and remind ourselves what those slant asymptotes are like. Okay? The slant asymptote, remember we said this whole thing can reduce down to an x squared minus 4 over an x minus 3. Again, the degree on the top is only one bigger than the degree on the bottom, so we have a slant asymptote. And remember, to find the slant asymptote, you divide and ignore the remainder. Okay? So I do here an x squared, and I'll make it plus 0x minus 4, divided by x minus 3. You could do this with synthetic division or with regular division. If I do it with regular long division here, x squared over x is just x. I multiply, so I have an x squared minus 3x. Then I subtract, and I get 3x, bring down the minus 4. 3x divided by x is a plus 3. So I multiply it down, 3x minus 9. I do the subtraction, and I get a remainder of 5. Now I don't care about the remainder of 5 because my slant asymptote will always be y equals whatever this is, in this case x plus 3. Okay? If you don't remember that at all, you can come by. I would be happy to go over that with you a little bit more. Okay, if that's a totally foreign concept to you. But what that will do for us in this case is that allows us to identify another thing that helps us determine the shape of our graph. So here is our slant asymptote. Okay? As you can see, everything that we have so far is in that like bottom middle quadrant here. Remember, the asymptotes, when you have whether a vertical and a horizontal or a vertical and a slant, it cuts the whole graph into like 4 sections like this. And unless that asymptote came from a double root on the vertical, you're usually going to have them kind of catty-corner from each other. Okay, so part of our graph is going to be down here. The other part was going to end up being up here, as we'll see. Okay? So, all of that is previous knowledge. Now we can incorporate what we saw before with our critical values, our sign diagram, and actually finding the max and min points, okay? So the sign diagram is what we saw up here, okay? And we see that it's increasing as we approach the hole, okay? Well, we also have the slant asymptote, so it's coming from very, very close to that asymptote up to the hole. Okay? And then it continues to increase through this 0 until we get to where the max is at a positive 0.76. Alright, so it goes through here, it goes through the y-intercept. At some point here it reaches a max when x is 0.76. So that right there we need to actually find the point for. Okay? We didn't do this before, but what is the actual point? Well, f of the 0.76 we can use our calculators for. Okay. So when we plug this in, we get 1.53 to 3 significant figures. Okay, so at 0.76 we're at 1.53. The y-intercept was at 0, 1, and 1/3. So 1.53 is just a little bigger than that. Okay, so we've now leveled off, and now it's coming back down, going through the other 0, and it's going to approach our vertical asymptote at 3. And it'll go down to negative infinity as it does that. Okay? So notice there, now we know 5 points or 4 points in a hole that help shape that along with those 2 asymptotes. Okay? Now, to find the min for the other part, we see that it's decreasing until we get down to 5.24. So 345.24. Somewhere in here at 5.24, we've got a min. Okay? Notice, by the way, this is why the sign diagram is important. What do you notice about your relative min compared to your relative max? Looking at it here.
On the other side of that.
It's on the other side of the asymptote. What about its value? It's going to be bigger, right? Now that's kind of counterintuitive. How can our minimum be bigger than our maximum? That's because it's a relative or local minimum and maximum.
That's why it's relative and local.
Yes. It's not an absolute maximum or minimum. This is a relative, which means in the neighborhood, it's the highest or lowest point. Okay?
So it's localized to the equation given into it, because that's not the actual huge. Like that's not the.
It's localized to the immediate vicinity. In other words, there's a change in direction there.
Yeah.
We were going up, now we're going down. Where's that point where we started to go down?
Mm-hmm.
It's right there at 0.76, 1.53.
Okay.
Okay? If we plug in the 5.24, what do you get?
Let's see.
Some of you have your calculators out now, but now you got to actually use them, okay? So plug in 5.24. All right, so 10.5, again, 3 sig figs,
Great.
10.5. So notice at 5.24, we're at 10.5. So that's going to be right about here. Now, we don't have any other points on this. All we have are the asymptotes to help us with the shape. So we know it's coming down from positive infinity. It's going to hit this minimum point, and then it's going to start going up as it approaches that slant asymptote. And there we have a really pretty accurate drawing of what this function will look like. Okay? Now, guys, the point of this is not just to be able to draw stuff that our calculator could do a whole lot faster. The point of this is to go ahead and understand what's going on at each of these values, okay? And there are a lot of things, that, like the hole, for example, if you aren't paying attention, your calculator doesn't give you a nice little visible hole. The pixels are so small, it looks solid there. So if you're not thinking, you're going to miss on that stuff, okay? And also identifying like the slant asymptote. Your calculator's not going to give you that. But also, what does this mean? This increasing, this decreasing? Well, remember, these are all rates of change. The derivatives are rates of change. So we can identify, hey, when is the rate positive? You know, when is our value going to be increasing? Because the rate is positive. And then as we get to using the second derivative, we can even look at, hey, how is the rate of change changing? Okay, that's our second derivative, the rate of change of the rate of change. And we'll be working with that more as we go forward here as well. Okay, so there's a pretty good sketch of this. Now, we've got some practice I want you to do. I want to look at one of these here that has the e to a power. Okay, notice it says find the position and nature of the stationary point. So basically, you're getting what the points are, so both coordinates. Don't just give me x equals whatever. But then also identifying, is this a max, a min, or a plateau point? And to do that, you would use the sign diagram, okay, first derivative test. So let's do B, okay? Let's do B. So first of all, what do we have to do?
Derivative.
Find the derivative, okay? So dy dx, to get the derivative, we're going to have to use the product rule because we have x squared times e to the x. So u prime times v plus u times v prime. What's the derivative of e to the x? E to the x.
Oh, over x.
No, that's ln of x. E to the x is e to the x. It stays the
Oh.
same.
Sorry.
Ln of x, the derivative is 1 over x. But, all right, so now we look at this and we say, okay, well, I see some common factors because remember, we want to set this equal to 0 because we want to find critical points. So I have x times e to the x times a 2 plus x if I factor out my common factor. So what are my answers? -2, 0. Anything else? What about e to the x? When will that equal 0? Never. There's an asymptote, a horizontal asymptote on the one end because it approaches 0 if you go to negative infinity. But that e to the x, this is why knowing your parent functions is so important. The range of e to the x is greater, or is that y is greater than 0. So that's never going to hit the x-axis. So I only get these two values. I set up my sign diagram. -2 and 0 go on my sign diagram. This is defined for all real numbers, so I don't need to worry about holes or asymptotes. Okay, so now I plug in different values into my first derivative in order to figure out what happens on my original function. Okay, so if I plug in, say, a -3 into my derivative, I have a -3 times e to the -3rd. I don't know what that is, but I know it's positive. So I don't care about that. So -3 times 2 minus 3 is -1. -3 times -1, positive. Okay? So this is positive, which means my function is increasing. Okay?
Yes.
Now I can plug in -1. -1 times a positive, 2 minus 1 is positive. So I have negative, positive, positive. That makes a negative, which means this is decreasing. And now I know that at -2, I have a local max. Okay, I'm not going to draw more arrows. That's going to get confusing. Okay, now that point we'll figure out later, but it's -2 something. Okay? So then we keep going with our sign diagram. I pick a number bigger than 0, so like 1. And that's a 1 times positive times 3. Positive. So I know my function is going to be increasing, which means I have a local min at 0. So the min is 0 something. I plug these into what? The original function. I'm trying to find points. Points come from the original function. So if I plug in a 0, I have 0 times 1, which is 0. So my origin is actually the minimum point on this graph. Okay, 0, 0. If I plug in a -2, okay, plugging in a -2, I would have -2 squared times e to the -2. that's gonna be 4 over e squared. And you can just leave your answer that way. It's exact. So 4 over e squared. If you were having to graph this, then yeah, as a decimal that would be a lot more useful, okay? But for right now, that's fine. You can approximate what that would be. 2.718 is gonna be bigger than 4 if you square it. It's almost 3, so if you square, I know it's gonna be like bigger than 4 but smaller than 9. Okay, so 4 over that, it's gonna be somewhere in the half to 2/3, somewhere like that. What was it? 0.541, okay. So, you can write it as the decimal or give the exact value. Okay? So that's how you would handle those, guys. Don't let the fact that you have e's or natural logs or whatever throw you.
It just seemed wrong.
It's all the same calculus.
For me, like, I understand like how you get to the end of the thing. I understand how to do it. I'm still a little confused as to what's the difference between an asymptote and a slant asymptote.
Well, asymptote is a generic term
Yeah.
for an imaginary line that a graph will approach but never touch.
Mhm.
There are 3 kinds of asymptotes.
Okay.
Okay? The vertical asymptote is when there is a 0 in the denominator.
Okay.
What makes the 0 in the denominator after you've already canceled out holes.
Mhm.
Okay? There's also the horizontal asymptote, and that's where that's going to be what it's approaching as x goes to infinity, and you find that using the Bobo-Botten and the ratio thing. Okay? So Bobo and also ratio if equal. Ratio of the leading coefficients if equal.
Yeah.
If equal degrees. Bigger on bottom, then y equals 0 if the degree is bigger. So you have an x squared over an x cubed, or an x squared over an x to the 5th. Okay? Now, other functions also have horizontal asymptotes, like e to the x or whatnot, but we're talking about like rational polynomial functions. But then you also had the slant, and these occur when it's bigger on top, so there are no horizontal asymptotes, but it's 1 degree bigger.
So Bobo-Botten still applies to horizontal.
Yeah, bigger, Bobo-Botten applies for horizontal, but that's also how you, if it's bigger on top, then you look, is it only 1 degree bigger on top, and if so, you divide and get your slant asymptote.
Okay. That makes sense.
Okay?